Alright, this is the first lecture of vibration. So the total hour only 16 hours. Um, the content of the whole lecture, as it's here. First, about the fundamental of linear vibration. Second, free damp vibration. It means the vibration that does not have the effect of damper. Forced vibration is a vibration that caused by external input as a force, and then 2 degree of freedom system, or 2 degree freedom of vibration system. Uh, this means if you have you have two mass, 2 point mass, or then those two mass have independent motion, then it means you have 2 degree of freedom. A multi-degree of freedom system is the system that you have multiple objects that have uh, independent motion. Okay. Not quite independent because they have interaction between them by force element like spring, like damper. So it's just that we need to describe their motion represented by different parameter, like something like that. Okay, and then a continuous system that actually you see all around you that have vibration, like in engine, car engine. So that the structure of the body of the engine itself is kind of continuous, right? You you touch it everywhere, it can have vibration. Not just single mass, as a whole. Um, I mean, not describe one single mass, the motion of one single mass as a whole, like that. That one is 1 degree of freedom, but it continuous. I mean, on the surface, each point of the surface of the body has vibration. So continuous along the body. Can be a road, and the road has a vibration, and to touch any part of the road, it has vibration. Or you can, I say you touch, maybe you can feel, but if you cannot feel, or you can feel but you don't know the amount of vibration, actually you can stick some sensor on the body at each part of the body, and that depend on that sensor. Maybe you can strain gauge or oscillator. From oscillator that can give you the acceleration at each point of the sensor that you put in, and then you can find the data of the vibration. Okay, first, fundamental of linear vibration. So there are 4 main points here. Oh, sorry, I think this is redundant. Redundant slide. Yeah. Um, yeah, in this fundamental linear vibration, we have 3 main points. First, free vibration, which means vibration that you just excite it and then you let it vibrate it by itself. There's no external force continuously uh, forcing it, okay, or drive it. Okay. Then number 2, force vibration. Like I mentioned, yeah, the car suspension, single suspension. If you the tire pass through the road which fluctuated, I mean at some part of the road they will a stripe that make the car vibrate, like, yeah, you have noticed that or not, especially on the road near near the school, near hospital, and then when they want the car to slow down on the road, they put the stripes, and so the car when the car passes through that, it's vibrate, right? So in that case, if you model only one car suspension, and you want to see the vibration of the mass of the car on the suspension, then the input is you can interpret it as velocity. So yeah, of course, the velocity that you can have here actually, of course, if the car has force to move, right? So that can be called as force vibration. And the last part is an energy method to derive equation for vibration. So mechanical vibration actually just motion, right? Motion that oscillate, uh, yeah, oscillates around some equilibrium point, and and the period to complete the one oscillation is called, yeah, the time interval to complete one oscillation is called period. How about frequency? How you call it frequency? It's just inverse of the period, right? The inverse of period is called frequency. Or you can say in 1 second you count the number of the complete cycle. Same thing. If the period is 2 seconds, it means in 1 second you only complete the half of the cycle. So you call the frequency is half. Right? But if in 1 second the oscillation complete in 10 times, okay, so it means the frequency is 10. So maximum displacement in vibration is the displacement from equilibrium position to the highest possible magnitude of the amplitude, right? So if the motion is restoring by 4 means, yeah, I said earlier that you just excite the system just a little bit and then let it vibrate freely, then it's called free vibration. Okay? Excite it, or you can say just sharp it, or just make the impulse force ding, and then let it vibrate freely. It's called free vibration. But if you keep hitting in uh, constant frequency, that is called force vibration. So the car engine run at a constant speed. It's called a force vibration. It's not free. But when you switch off, the duration from it starts to slow down until it becomes silent. Between that period is free vibration. Right? And if the motion of the vibration that we model and we don't consider the dissipation due to friction, we call it undamped vibration. So it is a very, very ideal case. Actually, it's not true. In real life, there's always frictions. There are always energy dissipation. Imagine that you have a very, very nice spring, and you want to you extend it, and then you have a mass, and you extend it and you release it. Ideally, we say it oscillates forever, right? We assume that there's no friction among the crystalline structure. So if we consider that there's no such friction, it oscillates forever. but it's not the case. There's always collision between crystalline inside, or maybe the bound between crystalline, the bound between different crystalline, and it generates some heat, some form of heat. Then the energy that you impose at the beginning will be dissipated little by little until it run out. Okay? When it run out, there's no motion anymore. Yeah, if the land power is very very small, and then we can just assume that it's ideal, and assume that the viscous friction is zero, or the damper effect is none. Okay, first let us look at undamped free vibration. So in this, there is a mass and spring. Um, when you are tied up a mass to the spring. Okay. So here is the initial length of a spring. When you are tied a mass and you hold it slowly, gently, hold it and let it go to the equilibrium point, and you take your hand out. It means it's stable there. Okay, that is called the equilibrium point. So it will extend a little bit from the initial length of the spring, right? And after that, you make a perturbation. Perturbation, I mean you push it a little bit, or you extend it a little bit, and then you release it. Then it vibrate. It starts to vibrate. And the equation governing this kind of system looks like this. How you can get this? Okay, Newton's second law. Whenever you want to apply Newton's second law, don't forget to use the concept of free body diagram. How can you use a concept of free body diagram? Okay, I don't like this guy. Oh, maybe it's good. I can put it here like this. Um, so you have the spring. What does the meaning of free body diagram terminology? Okay. So let's say here is the equilibrium point when we gently hold it and keep hold it well and leave it there. Then this is the equilibrium point. Then when you push it a little bit, just perturb it. Okay, by your hand. I cannot I cannot draw your hand well. You push it a little bit, then it start to vibrate. So to derive the equation, you use a free body diagram. You know it, free body diagram. Mhm. Body diagram. Yeah. What does it mean? It means you want to know the motion of that mass, bring that mass there only, and then all the force element you remove it, but represent it by force only. Spring is force element, right? Damper is also force element. If you have, but in this case you only have spring. So you don't put the spring here now because it's free body, but you represent the spring by the force on the spring. That's called free body diagram. And of course, you know that if the spring extends into the positive direction, and then the force must go to the in opposite direction, and it's proportional to the spring constant. Okay, and yes, suppose that you have all right. The I will explain the perturbation later. But now, just look at what force that act on that mass. So another force is g, that which is the gravity, right? Then you apply Newton's second law. The sum of all external force equal to a. Okay. Newton's second law, the sum of all external force, because all the spring element is substituted by just force, right? Then they are all external force. G also external force. Why mg is called external force? Because it's the force that generated by the earth. Earth will pull it, not itself impose the force, right? If you put on the moon, the force is different, right? Put it on the Mars, force is different. Of course, so this it means external. Equal to a. A means h double dot. Okay. So external, you use the direction h is like this, h dot and h double dot also like, yeah, point downward. Okay, this direction. So this one is opposite of h. It means it's minus kh. And this one g the same as h direction. It means g equal to um uh, there is something interesting that you can easily get confused. Uh, 8 plus kh equal to g. So sometimes you can see this equation. Sometimes you can see the right hand side is zero. So what happened here? Be careful when you model this kind of system. Uh, why? Let's say if I have the initial spring without mass and I label it from, if I label it here, zero here, if I label zero here, then this equation is correct. This equation is correct. Okay? Because actually you have call, we can call h, I call it h1. Um, yeah. So this equation means when you put the point mass and then you release your hand, it will fall down, oscillate around the g, around this equilibrium. This equilibrium. Okay? So different, so different phenomena. You are tied it to the spring and you immediately release it, it must fall down and oscillate. Correct? But if you are tied the mass to the spring and you hold it gently and let it move gently to reach the equilibrium and then you release it, it's there. It does not oscillate. Correct? So for the second case scenario, it means you label h0 in here. You got it? You label 0 here. It means uh, the gravity mg here is cancelled by what here already, by this initial displacement already. You got my point? So I can calculate h1 here actually is equal to g divided by k. This h1 from the initial length of the spring and release gently until it reaches equilibrium. You got that point? So it mean the equation here h dot double dot here equal to I can say h like this plus h1. dot dot. Yeah, but this one is 0. And also a kh here, h, yeah. What I mean is I let h equal to h plus h1. So I got this because h1 is constant. Yeah, h1 is constant. This distance. Then this one is 0. So this equation become um h double dot plus k h plus h1 equal to g. Then finally I can have h dot dot plus kh, and k times h1 equal to g. Then it can set g, and then you have this one is just 0 like this. So at this point, I just want you to be careful when you make a modeling of this. If you use the scenario as I explained, that when you apply the mass and you hold it gently and put it to the equilibrium, and then you release it. After then, you start to study the system. You put the force, you perturbate it, or whatever you do. Then you use this equation. Okay. So what does this equation say? Uh, what does this equation say? Okay. First, you know that you label 0 here, the direction of h like, yeah, capital H like this. You label 0 here at the equilibrium point. Okay, and what does this equation say? So if there's no external force, if you don't push it a little bit, I mean nothing happened to it after you release it gently like that. If there's no perturbation, the solution is always 0, right? It is 0, it equals 0 is the solution. You substitute here 0 and this 0 equals to 0. It's solution, right? But what if you make perturbation a little bit? Perturbation can represent by impulse function. Maybe you are not familiar with it, impulse function. Yeah, you push it a little bit and then let it vibrate freely. This is one type of experiment. Another type of experiment is you pull it to a certain distant edge. This edge, this capital H. You pull it a little bit and then you release it. So it means, what I want to say is the first scenario is if you start at 0, initial condition from 0, the solution is 0 itself. It's always 0 like this. But if you pull it by a distant edge and you release it, it vibrates, right? It means you are studying this equation, but with initial condition, it can at time 0 equal to a certain h0, maybe h0 which is not 0. You pull it a little bit and then you release it. So this equation will be different. The solution of the equation will be different because you start from something which is not 0. How you can solve this equation? Yeah, actually, h of t equal to what? Equal to h0 over k 1 minus e to the minus k over t. This is the solution. So when you at time 0 t equals 0, this become no. I mean mũi đỏ. I mean like this. So when t equal to 0, e to the 0 equal to, oh, there's no this one. Yeah. And sorry. Actually, I this is second order, right? Not first order. Sorry. So it should be cosine uh, k or square root there. I think yeah, square root t t0 become 1. Yeah, something like this. So put it literally this oscillate cosine represent the oscillation. Okay. Yeah, like this. So different. For this one, the solution is like this. For this one, solution is like this. Yeah, this one just explanation of how you can use Newton's law, second law to derive dynamic equation. Uh, well, this one is the explanation of inertia of a um, inertia of a point mass. But if you find you want to calculate inertia or point mass at another, not at its center, but at other points, for example, here with distance r, so the total inertia would be the sum of the inertia at the center of gravity plus the mass times the distance square. Okay, definition of inertia. Okay. So here, look at the motion free body diagram of this pendulum. Um, so you apply Newton's second law, but on the rotational motion. Rotational motion, it means the sum of all external moment or sum of all external torque equal to the inertia times angular acceleration. Okay. And here the external uh, force here produced by rotational spring. Okay, so rotational spring is K spring constant times the rotation angle. It's very similar to this equation. Okay? Very similar. It just that this motion is rotation. Okay, so you have the same um, form of equation, second order and constant coefficient like this. And you can do the analysis similar to this. Okay. Any question to this point? Maybe I go too fast or I go too slow. Is that okay? Yeah, don't hesitate to interrupt me if you have any question. So I continue with no question. Okay, and here there is another simple oscillator. You have a hinge joint here, and you have a spring at the middle now. Yeah, spring at the middle. Again, initial of point mass that what you calculate with respect to this hinge joint equal to the initial at the center of gravity plus inertia, mass time distance square. Distance is L. Okay. Um, so you derive the equation using Newton's second law. The external torque that imposed on this oscillator is uh, yeah, k time k time the displacement here. But the displacement here, yeah, the displacement here, because it's small, then you can reduce it to be the angle time the radius from here to here. The radius is a. So a time theta is the displacement at the spring, and if this become yeah, this displacement time the constant k, okay, this displacement time constant k become force, and force times this distance become torque or moment. So this is moment, and this right hand side here is j initial times angular acceleration. Okay, so finally you get this equation again. It has the same form as this one. Okay, second order. There's no damping term. Okay, second order. There's no damping term, and they oscillate according to the cosine function. Right. Any question? Yes, the hour is so exhausted. I'm supposed to be the one who get exhausted, but I talk all the time. Yeah, another oscillator for yeah. This one is just the way how you calculate the inertia. For a road, you need to compute the inertia. So finally, the inertia at the hinge point is equal to this. And the equation look the same because you have a spring here at the middle, not really in the middle, but the distance from the hinge point to the spring point here is b. So again you get this equation, same form. Second order. This one is torsional vibration. So the torsion, a rod can behave like a torsional spring. So the equation is second order because it's just spring, right? It's just spring. Then the equation is the same. But because this is torsional spring, the motion is rotation. Then you have the motion equation described by angle theta. So in the previous semester, you already studied about study the trigonometry. You understand all this kind of constant, right? Okay, so here how you can compute the equivalent stiffness of spring. Okay, yeah, the constants, the spring constant is called stiffness. So how you can compute the equivalent spring constant if you have two spring connected in series? connected in series like this. Yeah, be careful, not the schematic of the spring look like a resistant, but when they connected in series, the equivalent spring is not the sum of both spring constants, right? Be careful, but the sum of the inverse, okay, the inverse of the spring constant equivalent is the sum of the inverse of each spring constant. And for the two spring connected in parallel, then the equivalent of spring constant is the sum of the two spring constants. They're very easy to remember, right? Well, look at this. Uh, yeah, look at this structure. You can use the model in the strength of material. You can derive the equation of motion here or the equation of vibration here. It just become a second order. Always have the same form because we assume that there's no damper in the body. So you assume that once you perturbate it, it vibrates forever. It's like that. Yeah, so many model on the system that can have vibration, and for the ideal, for the assumption of no dissipation of energy, then they have the same form of equation, which is second order. That and there's no the term of first derivative, okay, or the second derivative and zero derivative. Always same like this. Okay, this one also, yeah, pendulum. Uh, yeah, pendulum also. The equation of motion of pendulum also second order. And the energy method can be used to derive vibration or equation of motion. So there's potential energy. Yeah, this is almost the last slide. I think. Okay, I think you are familiar with potential energy and kinematic energy this way. And the key point that you can derive equation of motion is to use the conservation of energy. Potential energy plus kinetic energy, which is mechanical energy, is always constant. So you add these them together, and then because it's constant, you take the time derivative, it must be zero, right? Then you can get the equation. This is also another way of deriving the equation. So you can get the same equation as the way that you use Newton's second law. So I finish this first lecture now. Yeah, by this slide. Yeah,